Hi, I am Kuldeep Purohit. I will be talking about rotating scalar fields and formation of Bose stars. So, first of all, I would like to thank the organizers for giving me the opportunity for giving me a talk on the project which we have been recently working on. So, let me begin. So, my talk is organized as follows. And So recently, formation of Bose stars has received understanding the process of formation of Bose stars has received a lot of attention. In 2018, Levkov et al. Paper have studied the formation of Bose stars in kinetic regime. It was followed by Chen et al. Paper where they have introduced studied the formation of Bose star in presence of self interaction. So what happens is that they take a cloud of axions, ultralight axions, axion-like particles or ultralight dark matter, which are interacting via gravitationally. Initially, by Levkov et al., it was taken as gravitational interaction among particles, and which will eventually collapse and form a Bose-like structure. Chen et al. Introduced self-interaction also among the particles, and which also collapsed and formed Bose-like structures. But this clouds, initial clouds, were not having any kind of intrinsic angular momentum among them. But it is natural to assume that those clouds must have some kind of angular momentum with them because of processes like tidal torque, gravitational shearing, etc. So we believe that it is important to study the star formation and process of angular momentum along with self interaction, and we will also study that if the stars are formed, then what are the properties of the formed bow star with respect to the Chen et al. Work and the Lepo et al. Paper. So we begin with the Gross-Pitarsky-Poisson equation. So in equation number one, if you see the right hand side, the first term corresponds to the quantum pressure, the second term is the gravitational pressure, the third term is the self-interaction term among the particles. So the equation number two is the Poisson equation, and these two are rescaled as the rescaling given here. So this is the equation which will govern the dynamics of the initial cloud. Okay, so it is not governing the bow star after formation, but initial cloud of bow star is actually governed by this, and it will uh, be the basic equation which we are working with. So the thing is that this psi here is the initial scalar field. So it is a field of scalar particles, and how this is evolved using this equation we will see here. So first of all, the thing is that we have to design the initial conditions. So we take a random distribution of particles. So how it is done and how we introduce the angular momentum, let's see in the next slide. So we have to design a wave function which is at time t is equal to 0, and it is a combination of two functions, phi1 and phi2. So phi1 is a normal Gaussian, and phi2, if you see, is the term which is actually responsible for the introduction of angular momentum, which is e raised to il tan inverse of y by x. So this is the term phi2 which is responsible for the introduction of angular momentum. So now phi is transformed. We take a Fourier transformation of this function phi, and then we multiply it with a random phase since we want a random distribution of particles. So this is how the random phase is multiplied in the momentum space, and this function is again back transformed to the uh, uh, normal r coordinates. So if we take here phi2 is equal to 1, then there is no angular momentum in the system, and this is similar to the work which was done earlier by Levga et al. So phi2 is the function which differentiates our initial condition with respect to the Levkov et al. Paper. So I want to show you. So the above panel which you are seeing is a normal random distribution of particles. But if you see the below figure, here angular momentum is introduced. So you can see a stretch uh, in the zy plane and xz plane. So this is due to the effect of that phi2 function which is introducing stretching, and this stretching is due to this angular momentum in the system. So we will be using this below panel type thing, so which are having angular momentum in the system, and we will see the evolution of such fields using this Gross-Pitarsky-Poisson equation. So I just want to pictorially show you that how the evolution of the field takes place. So the first figure here is the initial condition at time t is equal to 0, where you can see that particles are distributed, but there is a kind of stretch. And as the time proceeds, okay, the clumping has begun, and eventually at the end you can see a structure has formed. So this structure is the Bose star. Okay, so this is how this formation of Bose star takes place. Okay, we have done some analytic work. Okay, to put an upper bound on the coupling constant. So how much maximum self interaction can the field have? So we have some estimations on that. So for that, what we do is that we replace in this Gross-Pedatsky-Poisson equation the time derivative with omega phi, assuming that a stationary star has already been formed. So it is much after the condensation time when the star is formed. You can take the limit where I by dt is equal to omega, and we can also remove the spatial derivatives with 1 by L. So after doing this, we are having this equation number 3. So this equation is valid only when the star has already formed. Okay, so we are assuming that star is formed, and now this equation can work. Here the second term, as I told earlier, is the gravitational term, and the third term is the self-interaction term. Now, for a gravitationally bound structure to be formed, the gravity must always dominate, so the second term must always dominate over the third term. Okay, and when we take the this approximation, we get a condition that g by lb square should always be less than 1, and as long as this condition is satisfied, we'll be getting a gravitationally formed structure. Okay, and this result is consistent with our numerical simulations. Okay, we can also estimate the size of the Bose star which is formed. So from equation number 3, if we solve it for LB square, then we will be getting this estimation for the length of the bound state, which is the length of the star. And from this equation, it can be seen that G, okay, is less than 0 when it is having attractive self-interaction, and G is greater than 0 when it is having repulsive self-interaction. Please note this. So for attractive self-interaction, it shows that the star will be always less in size as compared to the repulsive self-interaction. So this is a crude result which we are getting right now just by seeing this, that the for attractive self-interaction, star will be more compact as compared to the repulsive self-interaction. So this result again is valid, is consistent with our numerical simulations. Okay, now for methodology, we are using this, we are solving this Gross-Pedatsky-Poisson equation using 6th order pseudospectral method, using by modifying the publicly available axionics code. And we have plotted vorticity magnitude to see that what is happening with the angular momentum in the system. And for g is equal to 0 and l equal to 0, it means that when there is no angular momentum and no self-interaction, our results are consistent with Levkov et al. Results. And to see that whether a star has formed or not, we are having two results, two checks. The first is that after a certain time, the density of the system will start increasing, which is a process of Bose-Einstein condensation has begun, and at that point of time, the seeding process of star has begun, and now it will grow with time. The second is by plotting the Fourier image. So I will show you that how these two tests look like. So let me take an example for repulsive self-interaction. So similar results we get for attractive and no self-interaction cases. So I'm showing you the result only for the repulsive self-interaction. So you can see that the top figure is when there is no angular momentum in the system. So initially there is a very low density, and after a certain time, the density has started growing. Okay, so this is the point where the star formation process has begun, and it will keep on growing. Okay, when we introduce the angular momentum to 3 in the system, okay, here you can see that the star formation has begun again, but it is a bit delayed with respect to the top figure. So as we introduce more angular momentum in the system, the condensation time increases here, and when we are having angular momentum equal to phi, it is further increased. So we can say that angular momentum hinders the star formation process, and it delays the star formation process. On the right hand side, the figure which we are seeing is the Fourier correlator function. So here a peak at negative omega is a is a representation of the formation of a bound state structure. And here also, if you see, there is a peak at negative omega. So all these three for angular momentum is equal to 0, 3, and 5. We are having a peak at negative omega, which is a sign that a star has formed. Okay. I also want to show you that how the mass of the star grows with time. So this top red curve is for angular momentum equal to 0, then L equal to 3, and then the green is for L equal to 5. You can see that for all times the mass is always greater for L equal to 0 than L equal to 3. And so as we introduce angular momentum in the system, we can say that the mass of the particles decreased. So it is not allowing star to become more massive. Introduction of angular momentum. And then we are having a similar result for attractive self-interaction. Also here also you can see that for angular momentum equal to 0, the star is having maximum mass, and for angular momentum equal to 5, the star is having the least mass. Okay. Now, these are the mass radius relations. So always we will start from the analysis from the tail. So you can see that when L equal to 0, the red curve. So as the mass grows, okay, the radius of the star decreases, okay, which is quite natural to see that as the star will grow more, will have more and more mass, it will get compact. Okay. Similar result we are getting for L equal to 3, but for L equal to 5 we are getting some unstable branch initially, and then we are having the same curve. Okay. So with introduction of L equal to for L equal to 5 for very high angular momentum, there is some mass shedding limit which is there. Okay. For attractive self interaction also, for you can see that for L equal to 0 and 3, okay, uh, we are getting the same pattern as for no self interaction, where the uh, as the mass increases, the radius decreases. And here also for L equal to 5, we are getting one unstable branch initially, and then it is following the normal pattern. Okay, but when we see the repulsive self interaction, then only L equal to 0 is the one, okay, which is having the normal thing, which is that as the mass increases, the radius decreases. But L equal to 3 and 5 follows a different mass radius relation from other cases. So there is something different happening at repulsive self interaction. Now let us see in more detail. So we are plotting vorticity magnitude. So this is the vorticity magnitude which is plotted over the density for attractive self interaction. So this leftmost figure corresponds to L equal to 0. This black contours which you are seeing are the contours of vorticity. So you can see that since there is no angular momentum in the system, so there are very less contours in the system. So since there is no angular momentum, when you see the middle figure where L is equal to 3, here you can see that all the contours are outside the star formation region, which means that all the angular momentum is outside the system, but there is no vorticity inside the system, which means that this is a stationary star which is not rotating. And this is the last rightmost figure is for L equal to 5, where again you can see that all the vorticity is residing outside the star. Okay, which again is a sign of formation of non-rotating stars. Okay, so for attractive self-interaction, we are not getting any rotation in the stars. This is also similar case we get for no self-interaction cases also. And this is the plot when there is repulsive self-interaction. So in repulsive self-interaction, we are actually plotting for L equal to 5, that how the vorticity grows with time. And here you can see that initially there is some vorticity, but as time proceeds, okay, the vorticity starts diminishing. Okay, and in the by the end of which is around 2 times of tau g, there is no vorticity in the system. Okay, which is a signature of a rotating star, that all the vorticity is inside the star. So this is a signature of a rotating boson star, which is also shown from the mass radius relation. Okay, so let me summarize the results. So we have done some analytical bounds on the value of self interaction, which is consistent with our numerical results. The introduction of angular momentum in axial cloud, as I shown, it will affect the condensation time, the compactness, the mass of the formed stars, as we have seen from the mass relations. Uh, and the variation of condensation time. And for the formation of rotating Bose stars, that if we want a rotating Bose stars, we must have repulsive self-interaction in this initial cloud, which was also shown by the Dmitry Levkov paper, which where they have done the stability analysis work, and where they have shown that for star to have rotation, stable rotating boson star must have repulsive self-interaction. So this is an agreement with those earlier results. Thank you.